Hi everyone, I'm John Boprosky and welcome to my webinar on how to create a perfect transmit feed-forward equalizer model from circuit data. Please type any questions into chat as I proceed with this webinar. I will also have a questions and answer session at the end of the webinar. You can also email me with your comments and questions at johnb@serdesdesign.com. Why is this webinar needed? High-speed digital integrated circuits and serializer/deserializer systems have their physical layer modeled and simulated in a channel simulator. Channel simulators are designed to use IBIS-AMI models that are based on the IBIS specification. Many commercial IBIS-AMI model generation tools cost tens of thousands of dollars to lease or to own. Today, the SerDes channel simulation technology has matured so that it is available for free using cloud-based tools at SerDesDesign.com. Included with the SerDesDesign.com tools are options to generate IBIS-AMI models from circuit data collected from SPICE circuit simulations. This webinar is to let you know about the process I've used for many years to create perfect transmit FFE models from circuit data, and it's available to you for free. I created SerDesDesign.com to enable me to create and deliver IBIS-AMI models to 40+ high-speed digital integrated circuit companies over the past 10 years. Over that time, I learned many processes that practically guarantee a better, more efficient, and automatic IBIS-AMI model building process using free tools. I learned how to create high-quality, low-cost IBIS-AMI models while avoiding the standard approach using high-cost tools. Along the way, I learned that expensive tools kill all chances you have of achieving low-cost, high-quality IBIS-AMI models. My tools are based on free tools: Microsoft Visual Studio, CMake, web browsers, HTML, JavaScript, and much more. I learned that creating IBIS-AMI models should be the last thing you concern yourself with when it comes to creating IBIS-AMI models. Focus on collecting the correct SPICE circuit simulation data and use automation. My tools rely on automation to generate models from measured and simulated circuit data. I learned how to escape the costly commercial tool trap that keeps most persons stuck in a permanent high-cost model creation situation. Many of my tools are available for free on the web at SerDesDesign.com with options to download and install local copies on your Windows PC. I'm here to share my learnings over the past 10+ years and introduce you to the same IBIS-AMI model generation capability I have used to create and deliver high-quality, low-cost IBIS-AMI models. What this webinar will show you: it will give you an overview of modeling SerDes systems in a channel simulator. Then I introduce the process I use to create perfect transmit FFE IBIS-AMI models for use in channel simulators. I give a real-world example for a transmit FFE IBIS-AMI model generated from circuit simulation data. Finally, I show you how you can get a free copy of my transmit FFE model generation tool for use on your Windows PC. Channel simulators are based on the IBIS Open Forum standard, currently at revision 7.2. This figure shows a typical SerDes system block diagram to be simulated using a channel simulator. The block diagram is generic for any channel simulator, but each tool has its specific way to represent this block diagram. The constituent parts of this SerDes system include the following: transmit IBIS-AMI portions. The AMI portion typically contains a transmit equalizer, often in the form of a feed-forward equalizer. The IBIS portion provides a differential output to the channel. Transmit package, channel, and RX package. These pieces represent the differential channel. Each part is optional and may be represented using S-parameter files. The RX IBIS-AMI portions have the AMI portion typically contains an RX continuous time equalizer, a clock and data recovery unit, and a decision feedback equalizer. The IBIS portion has a differential input from the channel. Modeling a SerDes system. The key channel simulator property to keep in mind is that it considers that the entire analog content, the green area in this figure, the total channel, between the transmit AMI portion and the receive AMI portion is linear and time invariant. As an LTI system, the entire differential analog section in the SerDes system is accurately represented by its single-ended impulse response. This key concept enables the channel simulator to achieve its fast simulation speeds. Creating a perfect transmit FFE model from circuit data. This model generation is from behavioral data that was, first of all, IBIS-AMI model generation from behavioral data was built into the SerDesDesign.com channel simulator from the beginning. I've used this process over the past 10 plus years, providing custom IBIS-AMI models to over 40 plus companies based on the circuit data they provided me. In today's webinar, I provide instructions on modeling a transmit SerDes FFE with circuit data. The modeling data is collected typically from a SPICE circuit simulator. The discussion is for a transmit series with an FFE only. Modeling a transmit series with other functionalities discussed in other SerDesDesign.com webinars. To start, let's talk about the typical SerDes system test points. This figure shows typical test points for a SerDes system. For the current discussion, test points TP0 and TP1 are used for data collection. NRZ data streams are used for modeling. TP0 is the NRZ waveform. The data collected at TP1 is the output impedance at the output differential pins and the time domain waveform at the output differential pair. The transmit SerDes differential output impedance is measured with an output load resistance of 50 ohms per pin, 100 ohms total. The S2P S parameter data with touchtone 1.0 format is collected at TP1 from 0 Hz to Fmax in steps of F steps, where Fmax is greater than or equal to 2 times the symbol rate, and F step is typically less than or equal to 10 megahertz. This data is collected for each transmit SerDes corner case. This data is used to create the transmit output IBIS buffer model as an S4P file based on the IBIS-AMI 7.0 specification or later. The transmit waveform data is collected at TP1. The modeling data is collected in the time domain. Even if the system is using PAM4, the modeling signal is NRZ. This NRZ waveform data is used to create the transmit AMI model and for NRZ verification. If PAM4 is used by the transmit SerDes, then additional waveform data may be collected using PAM4 signaling. This PAM4 waveform data is only used for PAM4 verification. The following pages discuss the data collection requirements. The SerDes output waveform data is collected at TP1 with load resistance RL for each corner case. The load resistance per pin is based on the S2P data from the prior slide at 0 Hz. Note that the load resistance per pin is equal to the characteristic impedance of the S parameters times the 1 plus SDD11 characteristic divided by the 1 minus the SDD11 characteristic, where the SDD11 characteristic is shown here. Here's the transmit FFE modeling concept. The FFE is assumed to have this circuit schematic model for an N-tap FFE. Each tap has its own delay, gain, filtering, and possible nonlinearity. The individual components are unknown, and the FFE is considered to be a black box, represented by its NRZ input waveform and its output waveforms into the defined differential load. The FFE black box modeling concept is discussed here. Define the maximum bit rate, define the waveform output sampling time step, which is typically 1 divided by the maximum bit rate divided by 32. Define the minimum bit rate to be at least 10 times smaller than the maximum bit rate. The waveforms are collected for each FFE state as discussed in the following pages. In the derived IBIS-AMI model, the tap gains and filtering are derived from the waveform data for each simulation for the specific channel simulator bit rate and samples per bit. For discussion purposes in this webinar, the FFE is assumed to have one precursor and one postcursor. Other cursor combinations are possible. Here are the transmit output waveform data details. The output waveform is collected using the minimum bit rate with an NRZ repeating pattern of 6 ones and 6 zeros as shown in this figure. A waveform segment 6 UIs long is captured to file with 1 UI before the precursor and 2 UI after the postcursor. The black box is the captured data. Here are transmit waveform data assumptions. For the FFE with one precursor and one postcursor, these assumptions are made. The precursor has K values, which can be positive or negative. Negative is the default. The postcursor has L values, which can be positive or negative, with negative as the default. The FFE has M drive levels. So, collect set 1 of waveforms for each drive level with the pre and post cursors set to 0. If M is equal to 14, then 14 waveforms are collected. Then collect the set 2 set of waveforms with the maximum drive level. Collect the waveforms with the negative pre and post cursor values. It is assumed that the positive pre and post cursor waveforms are inverted from that for the negative pre and post cursors. If K is equal to 13 and L is equal to 17, then 221 waveforms are collected. These assumptions result in collecting 235 waveforms for each corner case. The waveform file details are shown here. There is one file for each transmit SerDes state. The output file is a text file with 2 columns. First column is time. The second column is the transmit SerDes output waveform into the properly terminated load resistance based on the S2P SDD11 at 0 Hz. Use a file name that includes the transmit SerDes name, the corner case name, and the names of any control parameters. Here I discussed the processing of the transmit data. The transmit data collected on the prior slides is processed by SerDesDesign.com and described in more detail in a separate document. This discussion is just to give an overview of what we've done by SerDesDesign.com. The IBIS S2P data is converted to an appropriate S4P file and impulse response. This S2P4 file is used as the IBIS buffer. Each set of waveform files are combined into one file. All files should use the same NRZ pattern. All file data is checked to have the same time values with monotonically increasing time. All file data is interpolated as needed to have the same time values with time step of 1 over the maximum bit rate divided by 32. There will be 1 plus K columns in the combined file where K equals the number of files and contains all the original data. The IBIS buffer is represented with its impulse response and is de-embedded from the transmit waveforms. The de-embedded transmit waveforms are used in the AMI model. The IBIS-AMI model created is based on the IBIS 7.0 specification. The generated transmit IBIS-AMI model will be tested against the original transmit waveform data that was collected. Validation will show perfect agreement between the transmit IBIS-AMI model and the original transmit waveform data. Here are items for further consideration. This discussion was for an FFE with one precursor and one postcursor. If the FFE does not have any precursor and only one postcursor, then the waveform data collected is for the L postcursor states for each of the M drive levels, resulting in L times M data files. For other FFE tap precursor and postcursor combinations, similar steps can be defined for modeling the FFE as a black box, assuming output waveform data that results in a perfect agreement between the IBIS-AMI model and the waveform data. Contact SerDesDesign.com for modeling for these other FFE precursor-postcursor combinations. Converting the data to an IBIS-AMI model. The transmit IBIS-AMI model for discussion in this report is considered to be linear in time invariant, even though the waveforms collected may be inclusive of any circuit nonlinearities. It has an IBIS file that includes a model section with model type equals output. It has an IBIS circuit defined that is ignored because the one defined by the S4P file is used instead. The AMI file has reserved parameters that define the IBIS portion as an S4P file, using these three parameters as defined by the IBIS specifications 7.0 and later. Using the IBIS-AMI build project. The IBIS-AMI model building project is included in the SerDesDesign.com tool, SerDes IBIS-AMI Transmit FFE Modeling Tool. Use of this IBIS-AMI model builder tool is only dependent on the installation and use of the free Visual Studio tool. See the instructions included with the tool. This project contains these folders and files. Only 2 CSV files and 1 S4P file generated from the prior steps are required for the IBIS-AMI model. When the Visual Studio is run on this project, then the required IBIS-AMI files are generated. These files can be used in any channel simulator on the Windows PC. These are the AMI file, the IBIS file, the S4P file, and the DLL file. Use of the SerDes IBIS-AMI Transmit FFE Modeling Tool enables you to create any number of Transmit FFE IBIS-AMI models with the same licensing limits as the tool. Here's a customer example from NXP Semiconductors. So this process has been used many times to meet the needs of various customers over the past years. With NXP, though their transmit SerDes has a lot of detail, the modeling approach was by considering it to be a black box. And the model was based only on its output waveforms, as discussed in this webinar. The minimum bit rate was 1 gigabits per second, and the maximum bit rate was 28.0625 gigabits per second. And there are various control states. 3 corner states were included. The swing drive level had 14 states. The precursor had 25 states, 12 negative, 0, and 12 positive. The postcursor had 33 states, 16 negative, 0, and 16 positive. Combined, there are over 11,000 states per corner case. Simplifying assumptions were made as discussed in this webinar. Waveforms will be recorded while varying the drive level control parameter over its full defined 14 states with 0 precursor and 0 postcursor applied. Though the pre and postcursor states can be either positive or negative, and as agreed upon with NXP, only waveforms were collected for negative pre and postcursor states with reliance on the model for data interpolation and data gain inversion as determined by the model. Waveforms were recorded at the maximum drive level while varying the precursor over its 13 states, 0 and negative, and the postcursor states, 0 and negative, for each corner case. Here's what NXP Semiconductor said. All models had no issue or major or minor questions. The IBIS-AMI models delivered by John have worked well from first delivery in all EDA tools and for all bitrate ranges. They were generated in a timely and efficient manner. New features were easily added to the models. John was very successful working with a group that was disbanding and had less links to the design. There have been no issues or major questions, not even minor questions. This is by John Burnett, Signal Integrity Engineer at NXP. Using the drive waveform data. Drive waveform data is used to derive the nonlinear characteristics versus drive level. The upper figure shows the waveform data collected as the drive level was varied over its states, while pre and post cursor were at 0 for the typical corner case. The lower figure shows that the drive level varies non-linearly versus drive state. This nonlinear relationship is used in the transmit IBIS-AMI model to be generated using the pre and post cursor waveform data. This figure shows the waveform data collected for one setting of post cursor and a sweep of all precursor states. The meaningful data is bounded by the box. This data with the IBIS impulse response, the embedded, defines the AMI model. The AMI model decomposes this data into FFE gains and filter values defined in the modeling figure shown earlier in this webinar. This modeling is performed for the specific channel simulation symbol rate and samples per symbol. The SerDes.com process uses 3 directories. One is for the IBIS-AMI build directory, another is for the Transmit FFE Modeling Tool, and the third contains the circuit simulation files. The circuit simulation files included the transmit circuit output S2P data files for the 14 drive states and files for the 221 precursor postcursor waveform data files. The text files are assumed, but they can be any text file provided they have just the 2 columns shown here. The Transmit FFE baseband modeling tool has 1 executable, 1 batch file, and 1 file with user commands. Run this tool by selecting the batch file. The command window displays for the start and end of the tool are shown to the right. It shows the modeling process as it proceeds through each modeling process step. The tool includes a template for creating the Transmit IBIS-AMI model. The copy 3 files that were generated from the tool to the Transmit SerDes FFE baseband directory. The IBIS-AMI model generated results in perfect agreement with the data. So the tool includes the IBIS-AMI model development environment. All that's needed is the free Visual Studio tool that's discussed in the tool documentation. The figure to the lower right shows a perfect agreement between data and model. In summary, this webinar has shown you how to achieve a perfect data-based IBIS-AMI model for a transmit SerDes circuit with an FFE. These steps were discussed. Convert the S2P data to an S4P file and its equivalent impulse response. Combine the set of waveform files into 1 file. De-embed the S4P impulse from the output waveforms and generate a transmit IBIS-AMI model from the waveform data and S4P file. These steps are automated with the tool, SerDes IBIS-AMI Transmit FFE Modeling Tool. So here, I just want to introduce you to your Windows PC copy of my tool. It's the same process I have successfully used with my customers over many years. It automates the use of circuit simulation data in 1 step. It includes the IBIS-AMI model building environment, and it automates the creation of unlimited Transmit FFE IBIS-AMI models. Here's what you get. It As I said, it automatically does the conversion from S2P to S4P data. It automatically combines circuit waveform data into one file. It automatically extracts the desired waveform segment. It automatically de-embeds the IBIS response from the output waveform. It automatically generates the transmit IBIS-AMI model. The model automatically generates the transmit FFE taps and filtering whenever it's run with the channel simulator at the channel simulator specific bit rate and samples per bit. You can generate any unlimited number of transmit IBIS-AMI models. Okay, the tool includes instructions and examples. So check it out on my own dime. I personally guarantee that you will be successful using my SerDes IBIS-AMI Transmit FFE Modeling Tool. You have a full 30 days to put it to test for free. After that time, if you see the value in it, then you can buy it. I only want you as a customer if you're 100% happy with your investment. Simple as that. So, this is just another one of the premium tools available from SerDesDesign.com. The tool comes with a node lock time-based license. Use the tool free for 1 month. After you're happy with it, then you can decide to purchase a 12-month license. See the ordering instructions for your free web copy of this tool with this document, the SerDes Design Premium Tool.pdf. See the link below this webinar. And with this completes the presentation content of this webinar. I'll end the recording of the webinar and spend time with you to address your comments and questions. Remember, you can also email me with your comments and questions at johnb@serdesdesign.com. Thank you.